Hello, and welcome to our lesson on project execution and change management. In this segment, we will cover project execution, design stage. After we explored in the previous lesson the project conception and the project definition, starting with today's lesson, we will delve into the project execution. Project execution. The execution phase typically encompasses the design, production, or build, and implementation stages. However, the specific stages within each project may vary based on its intended purpose. For instance, hardware development projects may involve design, development, and production stages, while construction projects may include design and construction stages. In consulting projects, the stages could consist of background research and report outline, compilation, and presentation. Most projects resulting in a tangible end item, such as a product, building, system, or report, also incorporate an implementation stage. This is the phase where the end item is handed over to the user. Design stage. In the design stage, system specifications undergo transformation into plans, schematics, and drawings. The nature of the output varies based on the industry and the specific type of system, but commonly takes the form of visual representations such as blueprints, flowcharts, schematic diagrams, or models illustrating system components, dimensions, relationships, and overall configuration. Throughout the design process, the system is conceptually deconstructed into tiers of subsystems, components, and parts. Multiple design possibilities for elements in each tier undergo scrutiny for compatibility with one another and with elements at higher-level tiers. Additionally, they are assessed for their capacity to meet specifications, as well as system cost, schedule, and performance requirements. The hierarchical breakdown into tiers and components utilizes approaches such as block diagramming, requirements breakdown structure (RBS), and work breakdown structure (WBS). The design process consists of two closely intertwined activities. First, there is the development of a functional design that illustrates the system components and their relationships. This design activity aims to identify the logical and functional elements of the system and determine how they should be interconnected to achieve the system's objectives. This aligns with the core principles of the systems engineering process. The second type of design involves the creation of a physical design, detailing the actual appearance of the system and its components, including their sizes, shapes, and relative locations. This activity results in various types of drawings and models, such as engineering, manufacturing, and architectural representations. These detailed depictions are crucial for the subsequent stages of fabrication, assembly, production, and maintenance of the system. Occasionally, discrepancies between the functional and physical designs may arise due to assembly, maintenance, or appearance considerations, necessitating a revision of the functional design. The design process often follows an evolutionary, trial-and-error approach. A trial design is formulated, modeled, and then tested against system performance specifications. If it fails to meet requirements, the design undergoes modifications and retesting. This iterative design-build-test process is a common practice in the development of new or innovative systems. In the design of complex systems, iterations occur in multiple areas throughout the system, and changes in one subsystem can have cascading effects on others. The challenge is to minimize changes and design iterations for each subsystem, keeping redesigns localized to avoid interference with other subsystems. In many projects, the design and production or build stages do not follow discrete, sequential paths, but instead overlap. Construction or building of a system part may begin as soon as the detailed design for that part is complete, allowing the concurrent development of different sections. This practice, known as fast-tracking or design build, is common in construction, accelerating project timelines but posing potential risks. While fast-tracking can save time, problems may only surface after fabrication, leading to potential reconstruction and increased costs. The more traditional sequential approach, referred to as slow tracking, takes longer but allows for more comprehensive resolution of design issues before construction begins. During the design stage, the responsibilities of the project manager evolve. The project team experiences continual growth in both size and project activity as it progresses through the execution phase. With the refinement of the system and project plan, the project manager allocates project tasks to group leaders and subcontractors. As the project organization expands, the workload of the project manager proportionally increases. The intricacies of design activities necessitate collaboration from various groups within the contractor organization and its subcontractors. The project manager plays a crucial role in coordinating their efforts, fostering effective communication and interface, and striving to maintain alignment with the established schedule, budget constraints, and overarching system and project objectives. Interaction design. In an attempt to continually enhance the product, developers frequently add more features. This results in a cluttered interface, making it challenging for users to navigate and understand, contributing to what is commonly referred to as bloatware. Examples of commercial products, ranging from digital watches and cameras to ATMs and car consoles, are complex yet intended for use by amateurs rather than trained operators. The root of complexity and bloatware lies in product design being driven by engineers and programmers, who may overlook interaction design, the critical aspects of design encompassing product functions and their presentation to users. This oversight occurs when product goals and user requirements are unclear. The design process lacks guidance to meet user needs, and the user-system interaction is not a central consideration. To address these challenges, the project manager and systems engineer must maintain a focus on interaction design throughout the entire design process. This entails a comprehensive understanding of end users, including their preferences, skills, aptitudes, and behaviors with the product. Throughout the design stage, project reviews are conducted at key milestones to verify the fulfillment of objectives, requirements, and specifications. While these reviews are scheduled by the project manager, an ideal approach involves them being conducted and led by impartial outsiders. In the design phase, adjustments to initial designs may become necessary due to factors such as new technology, technical challenges, or evolving user requirements. These modifications impact work activities and influence project plans, schedules, costs, and budgets. Project management assumes responsibility for monitoring these changes, assessing their impact on the project, communicating these effects to relevant stakeholders, obtaining necessary approvals, and updating schedules, budgets, and plans accordingly. While design changes can contribute to increased project costs, the cost of addressing design-related issues during later production and operation stages is typically higher. Project management also bears the responsibility of ensuring thorough documentation of the design effort. Comprehensive documentation is essential to convey design requirements, features, configuration, strengths, and limitations to all stakeholders. This documentation serves as a foundation for creating plans and procedures for the subsequent stages of system production, operation, and maintenance. Planning for production or build and later stages. The project manager maintains a forward-looking perspective beyond the current stage, particularly during the design phase, where preparation for the production stage begins. The planning for production encompasses tool and machine design, procurement of equipment and materials, assembly processes, functional tests, component tests, integration tests, packaging, and more, all detailed within a comprehensive production or build schedule. Due to the possibility of incomplete design materials, specifications, drawings, etc., by the scheduled time, production tasks may need to be phased, necessitating coordination between design and production tasks. The overarching plan for the production or build stage must also consider the systems, tasks, and resources essential for producing, operating, and maintaining the end item system. These crucial elements, referred to as side items, are distinct from the main contract end item of the project, but are equally indispensable. This is the end of this segment of our lesson. In the next segment, we will discuss Production Build Stage. This course is presented to you by South Europe College. Thank you for listening, and see you on our next segment.